So let's look at the rules for drawing Lewis structures. Here on the page in front of you, you have 7 rules for drawing Lewis structures. If you follow the rules as they're laid out on this paper and go through all of the videos on the topic, there is no reason that you can't get every single question correct. Lewis structures is definitely a topic that you will need to know as you go on to Chem 2, organic chemistry, biochemistry. This is a very important topic in the scope of chemistry. Rule number 1 says to calculate the total number of electrons by adding the number of valence electrons for each atom. For a polyatomic ion, the charge must be included in your calculation. You'll subtract 1 electron for each positive charge and add 1 electron for each negative charge. Remember that the number of valence electrons for each atom comes from the periodic table. If we write the electron configurations, we can get that information. If we look at the older group numbers on the periodic table, we can also get that information. So do you know how to look at the periodic table, determine the number of valence electrons for each of the atoms in this structure, and then calculate the total number of electrons that will be in their Lewis structures? Go ahead and pause the video and try. Determine the total number of valence electrons for the Lewis structures in each of these compounds. HCN is the first one. When you look at the periodic table, hydrogen is in group 1A. That means it will bring 1 valence electron to this structure. Carbon is in group 4A and will bring 4 valence electrons to this structure. Nitrogen is in group 5A. It will bring 5 valence electrons to this structure for a total of 10 valence electrons in our Lewis structure. For the compound with NOF, nitrogen in group 5A brings 5 valence electrons to the structure. Oxygen is in group 6A and brings 6 valence electrons to the structure. Fluorine is in group 7A and brings 7 valence electrons into the structure for a total of 18 valence electrons in our structure. CH4, or methane. The carbon in group 4A brings 4 valence electrons to the structure. Hydrogen in group 1A brings 1 valence electron to the structure. There are 4 hydrogens, so we need to count the valence electron that each hydrogen brings to this structure. So my calculation for the total number of electrons looks like this. I have 4 electrons from the carbon. I have 4 hydrogens that each bring 1 electron, giving me a total of 8 electrons. The ammonium ion, NH4+, this is a cation. So the fact that we have a positive charge here tells us that in the entire structure there is going to be 1 more proton than electron. That means that as we calculate that total number of electrons, we're going to need to come up with a correction for the number of electrons based on the imbalance between the protons and the electrons. My nitrogen is in group 5A. It will bring 5 valence electrons to the structure. My hydrogens are in group 1A and will bring 1 valence electron to the structure, and there are 4 of them to account for. That gives me a total of 9 electrons that would come from all of these atoms for the structure if I had a neutral compound. But because I have a cation, I need to make an adjustment. And again, my cationic charge tells me that there's 1 more proton in the structure than electron. So the correction I need to apply is to subtract 1 electron from this total, and that gives me 8 electrons, which will be the total number of electrons that I use in my Lewis structure. Anytime I ask you to calculate the total number of valence electrons for a Lewis structure, it includes this correction. So the answer to that question for the ammonium ion would be 8. We also have the nitrite ion, NO2-, so that as we look at the nitrite ion, my nitrogen brings 5 valence electrons to the structure. I have 2 oxygens that each bring 6 valence electrons to the structure for a total of 17 electrons from the atoms. If this compound were a neutral compound, that would be my total number of electrons. But because I have an ion, I need to make an adjustment to the number of electrons. I have an anion, So that tells me that in this structure, there's going to be one more electron than proton. So that my correction to account for the charge means I'm going to take the 17 electrons I counted from the atoms and I'm going to add in one additional electron for my negative charge, and my total is going to be 18 electrons. Again, if I ask you to calculate the total number of valence electrons for the nitrite ion structure, the answer is 18, which includes that correction from the negative charge. Rule number 2 says to identify the central atom of the molecule. You will connect the other atoms to the central atom with a bond and then calculate the number of electrons that remain. The least electronegative atom is often the central atom, and hydrogen can only ever have one bond, so it will never be the central atom. All of the molecules that we deal with on this topic will have a central atom. That means that one of the atoms will be in the middle and the other atoms will be outside. So if we have a generic atom, X, that's going to be in the middle of our molecule, and that atom might be bonded to A, something like that. This would be a molecule that has a central atom where X is that central atom, or my inner atom, and then the A's are my outer atoms or my terminal atoms. I want you to determine the central atom for each of the compounds that you see here. You're going to do that based on the fact that we know the least electronegative atom is most often the best candidate for our central atom, and we know that hydrogen can never be a central atom. So those two factors should allow you to determine the central atom for each of these compounds. Pause the video and do that. Here you see the answers. For HCN, hydrogen cannot be a central atom. That leaves our choice to be between carbon and carbon is less electronegative. For NOF, these are 3 of the 5 most electronegative elements on the periodic table. Nitrogen is the least electronegative, which makes it my best candidate for a central atom. NO2 minus, for the nitrite ion, again, nitrogen and oxygen are both among the 5 most electronegative elements on the periodic table, but nitrogen is less electronegative than oxygen, making it my best candidate for the central atom. For PCl3, chlorine is among the 5 most electronegative elements on the periodic table. Chlorine and phosphorus also appear in the same period on the periodic table. So we can either use the trend or the ranking of the top 5 most electronegative atoms in order to conclude that phosphorus will be less electronegative and our best candidate for a central atom. For BCl3, again, we know that chlorine is among the 5 most electronegative elements on the periodic table. Boron is not. So that means that boron is going to be our best candidate for the central atom. For the ammonium ion, NH4+, we know that hydrogen can never be a central atom, so my only candidate is nitrogen. For HPO2, hydrogen can never be a central atom. Oxygen is among my 5 most electronegative atoms, therefore I know that it will be the phosphorus as my best candidate for the central atom. SOCl2, I know that both oxygen and chlorine are among the 5 most electronegative elements on the periodic table, making sulfur my best candidate for a central atom. Rule number 3 says to complete the octets for outer atoms by calculating the number of electrons that remain. And remember that as you complete the octets for your outer atoms, hydrogen only ever has a duet, and hydrogen will achieve that duet through one bond only. Hydrogen will only ever form one bond. Rule number 4 says to put remaining electrons on your inner atom and then calculate the number of electrons that remain. Rule 5 says that if your inner atom does not have a complete octet, we will make double or triple bonds. Rule 6 says to be sure your structure has the correct number of electrons that you calculated based on step number 1. Rule number 7 says to be sure that each atom has the correct number of electrons, meaning that hydrogen can only have a duet and most other atoms will have an octet. Now, if we look at some examples to begin understanding the rules. Let's look at water as our first example. And water is a good first example because you probably already know the structure of water. That means that as we go through the rules, we can follow the rules and understand how the rules will apply to a structure that, again, we're already familiar with. So when it comes to adding up the total number of electrons, the atoms that we have are hydrogen and oxygen. And so each of those atoms are going to contribute a number of valence electrons. When it comes to the hydrogen, we have 2 of them that we will need to account for. And so we'll have 2 hydrogens where each of them will bring 1 valence electron to the structure. My oxygen from group 6A is going to bring 6 valence electrons to the structure, giving me a total of 8 electrons in the structure. The structure that I draw must have exactly 8 electrons, nothing more, nothing less. Exactly 8 electrons. So this is my total number of valence electrons that I have for this structure. My next step, number 2, tells me to identify the central atom in the molecule. And so between hydrogen and oxygen, I need to make a choice on my central atom. This is an easy choice because one of the things we discussed with rule number 2 originally is the simple fact that hydrogen cannot be a central atom. That means that in this structure, my oxygen will be in the middle and I'm going to bond my 2 hydrogens to it. Now, in doing so, I put 2 electrons into this single bond and 2 electrons into this single bond. So that means that I've already incorporated a total of 4 electrons into my structure. So I'm going to subtract these electrons from my structure, and that tells me that I have 4 electrons left in order to complete my structure. As I move on to rule number 3, I'm going to complete the octets for my outer atoms. In this case, my outer atoms are the hydrogen atoms that I have, and I know that hydrogen will only ever have a duet. So my hydrogens are happy with the 2 electrons in the single bonds that they each have, so there's no electrons to add to those outer atoms. Rule number 4 says to put remaining electrons on your inner atom. My inner atom is the oxygen, and right now I have 4 remaining electrons. So that means I'm going to put those 4 electrons on the oxygen in the form of 2 lone pairs. I just put those electrons into the structure, and so as I subtract them, I have 0 electrons left, so I know that I have incorporated all 8 electrons into this structure. As I look at my structure for water, and I look at the rest of the rules, rule number 5 says to look at my inner atom. If it doesn't have a complete octet, I'm going to make double or triple bonds. But in this structure, I see that the oxygen has 8 electrons, so rule 5 will not apply. Rule 6 and 7 want me to double check my work. I have exactly the 8 electrons I calculated in this structure, 2, 4, 6, 8 electrons, and every atom has exactly the number of electrons that it is looking for. This is my Lewis structure for water. When I look at the way that each of the atoms in this structure see its electrons, hydrogen is going to see its electrons in the form of a duet, which comes from the 2 bonding electrons we see there. The oxygen in this structure is looking to achieve an octet. And in this structure, it sees this octet in the form of 4 bonding electrons and 4 non-bonding electrons. And those 4 non-bonding electrons make up 2 lone pairs. My hydrogen here also sees the duet with 2 bonding electrons.